So thank you, Mark and Lars, for the invitation. But I actually want to begin by thanking the friends of KITP. So Lars said, thank you for continuing to be friends of KITP. I say that myself. I first came to KITP in 1994. At that time, it was the ITP. And it was an amazing place to come as a postdoc, but it is at least twice as amazing now in basically every measure. I happen actually to have been here. I didn't look up the year. You could figure out the year. I happen to have been here sitting outside on the lawn at the event where it was announced that Fred Kavli's gift was going to turn it from the ITP into the KITP. So I happened to be here when David Gross and Fred Kavli announced that, whatever year that was. But this is the first time I've been here since the Munger residence has been part of the KITP, and it is amazing. I see a number of my colleagues here who are like me staying in the Munger residence. They would all say the same thing. Looking forward to seeing the new building in, year did you say, 2028? So that's about real estate, but in terms of people, it's an amazing place to come. This really is, you know, if you think of the whole universe of theoretical physics, this is one of the brightest stars, possibly the best place to come in the world of theoretical physics, and that owes so much to all of you. So I want to begin by adding my thanks. So, hot and cold quark soup under pressure. The title is the introduction. I'm going to first explain the word quark, then we'll get to soup, hot and cold, and under pressure. Over the course of the first half of the talk, you'll understand every word in the title, and then I'll tell you about where we're going for the second half when we get through the first half. So quarks are the answer to the question of what are protons made of. The answer to this question is quarks. And this was the central question in fundamental physics in the 60s, and it was very confusing because by that time, dozens of cousins of the proton had been found, and their patterns had been studied. And just as Mendeleev had looked at the pattern of atoms and had drawn conclusions, people were looking at the patterns of all of these particles, and it was as if they were made of quarks. They had been named. Protons seemed to be made of 2 ups and a down, and neutrons seemed to be made of 2 downs and an up, but nobody had ever seen one. And still to this day, nobody has ever seen one quark all by itself. So what was going on? At the end of the 60s, Friedman, Kendall, and Taylor tried to answer this question in the same way that Rutherford discovered nuclei by shooting alpha particles at atoms and saying, hey, they bounced off. That tells me there's something hard in the middle of an atom. These folks said, let's take the brand new Stanford Linear Accelerator, which is 3 kilometers long, and shoot an electron beam at protons, and let's see if the electrons ever bounce off at large angles, just like Rutherford did. Most people were not asking that question. I've made it sound like an obvious question. It wasn't obvious then. It wasn't obvious then because if an electron bounced off a proton, it blasts it into smithereens. Is that really a good way of learning what's inside a proton? Turns out the answer is yes. So they did the Rutherford experiment with an apparatus. This is a diagram of it. The electron comes in from the left, and the poor unsuspecting proton is sitting right about there. And these are the apparatus to look at the scattered electron. This is what it actually looks like from the late 60s. There's a person down there. And this is the cartoon of what they were doing. Here's the proton. There's the up, 2 ups and a down. The electron comes in. It scatters off at large angles, and it blasts the proton into smithereens. It blasts the proton into smithereens by kicking this up quark enormously with high energy off to the right, and the electron comes flying off. And Friedman, Kendall, and Taylor looked at that electron, did a quantitative analysis, and said, we see quarks. It was just as real as Rutherford seeing nuclei. Quarks were in there. But in a sense, this added to the confusion, because if they could see quarks in there in this way, why could nobody see a quark by itself? So this confusion was resolved in 1973 by 3 people, one of whom you all know, David Gross. So in 1973, David Gross and his 2 colleagues, Frank Wilczek and David Politzer, discovered the fundamental laws of nature that tell us how quarks behave. these laws are called QCD. That's just 3 letters. It doesn't matter. But what they did is the analog of what Galileo and Newton and Einstein did for gravity. It's the analog of what Coulomb and Ampere and Faraday and others did for electricity and magnetism and light. They found the fundamental laws that govern quarks. This resolved the prior confusion, which I'll explain how it resolved that in just a second. It provided a quantitative description of everything we know about quarks, and it's a core part of our understanding of the universe today. And anytime anybody makes a discovery of this magnitude, it opens entire new vistas to investigation, and everything in my talk lives within the vistas that were opened by this discovery in 1973. So let me briefly explain how they resolved all the puzzles. Quarks and gluons are not so different from electrons and photons. Electrons I've mentioned, photons are the particles of light. Gluons are exchanged back and forth by quarks. That's how they interact with each other. So just as electrons have charged and charged particles interact with each other by exchanging photons, photons are governed by Maxwell's equations. That's the physics of electricity and magnetism and light. Quarks have a new kind of charge called color by physicists from the 1960s. Quarks, anything colored interacts with each other by exchanging gluons. Sounds boring. It's just same stuff, different words. Gluons described by something that looks like Maxwell's equations. The only difference is that the gluons themselves are colored. Photons are neutral. When we are seeing each other, the photons going back and forth between us have no charge, but gluons have color. And that sounds like a technicality, but what Gross, Wilczek, and Politzer showed was this technicality has consequences. And what they showed is that because of this technicality, and I won't explain how they showed it, the force law between electrons is just 1 over r squared. That's Coulomb from the 18th century. And that means that the force gets stronger as you take electrons closer to each other. It gets weaker as you take them farther away, like 1 over r squared. It's different for quarks. When you put them close together, the force between them grows, but it grows more slowly than 1 over r squared. So quarks are said to interact weakly because as they get closer together, the force doesn't blow up this fast. It blows up less fast. What if you pull quarks far apart? Well, if you pull them farther apart than some capital R, the force between them gets so much stronger than Coulomb that it stops falling off. If I take 2 quarks and try to pull them apart, once they get farther apart than R, it's like as if there were a rubber band between them. Constant force is like a rubber band. So these laws have a length scale inside the laws called capital R. What's capital R? It's 10 to the minus 15 meters. That's the size of a proton. So the fundamental laws that David Gross and his 2 colleagues discovered tell you immediately the size of the proton. Further consequence, if you kick a quark really hard here, so think about this. I kick this quark really, really hard. It's going flying off to the right. Whoops, sorry. That was not supposed to happen. Where are we? Here we go. I kick this quark really hard. It goes flying off to the right. As this quark is going flying off to the right, it's as if there was a rubber band connecting it to the other debris. That rubber band stretches and breaks, and this is a very pictorial and hand-waving way of explaining all this debris, the smithereens here, is the shards of the rubber band. It is as if there was a rubber band and you smash this up quark, and instead of getting just an up quark coming flying out, you get lots and lots of debris which comes from the breaking up of that rubber band. I'm obviously describing this in a very hand-waving way, but the laws are precise and predictive. I'm not doing them justice. And from these laws, it was immediately understood why all the cousins of the proton have the same size. It's that R. It was immediately understood why Friedman, Kendall, and Taylor could see quarks in a proton. That's because when they shot that electron at enormous energy at the proton, they were taking a picture of where one quark is in a very brief instant of time. They were doing a high-resolution photograph, and at short length scales, quarks are weakly interacting. The equations, I said, are quantitative and predictive, but they're hard to solve, and it took a long time, 35 years in fact, and supercomputers, to use these laws to calculate the masses of the proton and its cousins, but that was done by 2008. And Well, I said a new discovery like this opens new vistas. Those vistas were already clear by immediately after 73. In 1974, these two physicists, Collins and Perry, they wrote a paper with quark soup in the paper. The phrase quark soup from my title first appeared in the scientific literature in 1974. They realized that if you could take an entire star's worth of protons and smush it down to about 10 kilometers in size. How can we do that? We go ask Lars. That's called a neutron star. Lars is an expert. We can't do that in a laboratory, but nature does it. The radius of a neutron star is about 10 kilometers. The radius of the sun is about 7 times 10 to the 8th meters, 7 times 10 to the 5 kilometers. That's the factor you need. So Collins and Perry said, maybe there's quark soup in the middle of a neutron star. This is a very exciting area of scientific exploration today, and I'm going to come back to this at the end of my talk. This will be the cold quark soup in the title. It's under great pressure because the entire weight of the star is squeezing it in.
What was the previous slide that you skipped over?
I don't think I skipped anything.
Yeah, you did.
Oh, this is showing the theoretical calculations of the masses of all of the cousins of the proton, and theory agrees with experiment. This was in hand by 2008. It took 35 years to do this calculation, but by 2008, we know that the fundamental laws of David Gross and friends describe the masses of all of those cousins of the proton that were so puzzling in the 1960s. Okay, so also, in this case, there's not like one paper to point to. Collins and Perry, 1974, cold quark soup. By the mid-70s, by the work of many, it was hot quark soup. It wasn't called that. It's what we're going to talk about. It wasn't called hot quark soup at the time. But it was realized by the mid-70s that at high enough temperatures, protons and neutrons cannot exist. Matter, this is what was the thought in the 70s, must be a gas of quarks and gluons. It's at high enough temperatures. It was this stuff was named quark-gluon plasma, gas of colored particles. And again, mid-70s, people realized the temperature had to be above 2 trillion degrees. So hot that there are many, many quarks and gluons in the volume of what would be a proton. And the only place where such temperatures arose is in the Big Bang. So already, just a few years after David and his colleagues' 1973 discovery, people realized that we all of a sudden have a chance to answer, where did matter come from? How did the first protons form? And nowadays, one often sees cartoons like this. This is the universe today. To the left, it's going back in time. Galaxies formed at this time. Atoms formed at this time. This is 300,000 years after the Big Bang. Nuclei formed 3 minutes after the Big Bang. And protons formed here, 10 microseconds after the Big Bang. So we will be talking about physics that happens around here, 10 microseconds after the Big Bang. Earlier than this, quark soup. Later than this, protons. So by the 1970s, it was understood that we have the ability to ask questions about the very, very early universe using fundamental laws of nature that had been discovered. I told you it takes a long time to do these calculations. It took until 2010 to calculate the pressure of hot quark soup. These are calculations from 2010 showing the pressure of hot quark soup as a function of temperature in some units that I'm going to demystify in a second. You can see that the pressure of hot matter changes dramatically at a temperature right around here at around 150 MeV. What is MeV? This is 1.7 trillion degrees. To the left of here, below 1.7 trillion degrees, protons. To the right of here, you can see it's a sort of continuous transition. There's not a sharp line. That's why I put a wiggle there. But this is quark soup. You can see its pressure. So let's try and put numbers in compared to pressure. We know 5 trillion degree quark matter, which is right about there, 5 trillion degree temperature. That's a couple of microseconds after the Big Bang, and it's 2 times 10 to the 31 atmospheres. There's the other program here. Is anyone here from the other program? I've got some of my colleagues here from the program I'm here for, who I'm going to point to at various points. Nobody here from the other one? The other folks here are studying geophysics. So I added this to the slide. The stuff we're talking about has 7 times 10 to the 24th times the pressure at the center of the Earth. So we're looking at high pressure matter much, much higher than their high pressure matter. So is this a gas of quarks? Is this a gas? Everyone assumed it was a gas since the 70s. But understanding what it is actually like had to wait until scientists reproduced it in the laboratory. By accelerating and colliding lead nuclei at an accelerator, scientists started making droplets of hot quark matter, droplets of the Big Bang. In 1983, Veit Busha, who is a friend and colleague of mine at MIT, and his colleague Goldhaber, they calculated in 1983 that if you want to make a drop of quark soup, they didn't call it that, but if you want to make a drop of quark soup, you need an accelerator with this energy. That was 100 times greater than any accelerator that humans had built in 1983. They said, we want to get to this energy. In the year 2000 in Long Island, the relativistic heavy ion collider began doing collisions at twice this energy that they had identified. And since 2010, the Large Hadron Collider at CERN near Geneva achieves energies that are 27 to 50 times this energy. So these two facilities, one in Long Island and one in Geneva, are really recreating the Big Bang. But that's not right, because you collide two nuclei, you're recreating little bangs. You are making the stuff of the Big Bang, but not a universe worth of it. You're making the stuff of the Big Bang in a tiny little volume, about 10 to the minus 14 meters in size, and it then promptly expands, cools, and explodes. This is one of the earliest photographs from Rick, roughly the year 2000. This is the debris of an explosion that occurred right there when two gold nuclei collided. One was going into the board, one was coming out. They smashed into each other there, and they made about 1,000 particles, which you see. So now we have to be forensic scientists. We have to look at this debris of the explosion and see if we can learn anything. And I'm going to train your eyes so you can look, not at this one, but you can look at the debris of, in 5 minutes, you'll understand how we just made a big discovery from looking at debris of explosions like this. By today, the energy frontier is at CERN in Geneva. This is the Large Hadron Collider, drawn onto a satellite view of the environs of Geneva. This is the airport runway. CERN, the offices and where I sit when I'm at CERN is right in around here. Guy works at CERN. Alba has worked at CERN. Samuel has worked at CERN. There's many people here in the room who are CERN folk, are or recently were. When I go to CERN, I like to live in this little village right there. The Sunday market here is one of my the scientists think I come for the science. The Sunday market in this village, that's part of why I go.
What's the name of the village?
Thoiry. Sorry, Thoiry. I have to switch into French. So you accelerate nuclei, some going around this way, some going around that way. They collide at 4 points. You have cameras at those 4 points. This is inside that tunnel. This is the accelerator. At 4 points, collisions occur. You need cameras. This is a camera called the CMS. So lead nuclei come in from this side, they collide here, and this takes a photograph of the collision. This was obviously a diagram. This is the real thing. Here's another one of those cameras. This one's name is Elise. This is a photograph of the collision. Right in the center there, a lead nucleus coming from here and a lead nucleus coming out of the board collided. This makes 30,000 particles, not just a few thousand. So this is data. This is what you look at. First collisions at CERN in 2010, and I just put little icons from all 4 of the cameras, actually from 3 out of 4 of the cameras, just to not leave anybody out. Okay, so these collisions really are making little drops of the Big Bang. But what we see is the debris after the explosion. So how can we learn about the behavior? What have we learned? Big surprise. This surprise developed between 2000 and 2005. This surprise came from Rick. This was understood before the LHC began its work. By 2005, scientists looking at pictures like the ones I've shown had realized that this trillions of degree hot quark matter is a liquid, not a gas. So it's soup. That's why I'm calling it quark soup. And there's irony in this. Rutherford, for those of you who know the history of Rutherford, he thought atoms were made of some sort of a pudding. And he shot his alpha particles at it and was shocked to find nuclei. Freeman, Kendall, and Taylor shot the electrons at protons, and they were really quite surprised to find those hard point-like quarks inside. This is a surprise of the opposite character. People were expecting a gas, and instead they found soup. This soup turns out to be very, very liquid-like. There's a quantitative measure of how liquidy a liquid is. And it has to do with, as a liquid flows around a corner, how much internal friction is there in the liquid. This is called the shear viscosity at a certain unit, which I won't describe. It turns out that hot quark soup, when you use the right units, has the lowest shear viscosity of every other liquid that's ever been studied by humans except one, which comes close. And as Mark said, the strength of that, the interactions between the little bits of liquid are what make it such a good liquid. So it's called a strongly coupled liquid. This discovery, circa 2005, is what, every discovery opens new vistas. This one did also. If this stuff had turned out to be a gas, we would have studied it, declared victory, and we would have been done. The fact that it's a liquid is what's made it interesting, and it's what's worth telling you the remaining 20 years of the history that I'm going to tell you. So how was this discovery made? It was not made the Rutherford style. So how was it made? I'm going to tell you how to make this discovery. I'm going to teach you to make it with your eyes. And I'm using data initially not from trillion degree hot matter, but 10 to the minus 9 degree cold matter, ultra cold clouds of atoms. This is a completely different style of experimental physics. They're done in laboratories I don't know, do you have cold atom experimentalists at UCSB? Yes. Who should I name a person? I don't know him, I'm afraid. I know my colleagues at MIT who do these experiments. These photographs are from an experiment that was done at Duke in 2010. This is a cloud of cold atoms trapped in a cigar-shaped trap, and then you turn the trap off so the thing explodes. And this is literally a series of photographs of the explosion. So there's a cigar-shaped cloud of atoms. You release the forces holding it in, it explodes. And suppose this was a gas, what would happen? If this were a gas, in a gas, every atom is moving in random directions. As you let this thing explode, there'll be atoms going in every which way and just as much up and down as left and right. And you can just see with your eyes that all the atoms are going left to right. It's cigar-shaped, so they're going in the equatorial direction. That is what liquids do. Because how do you think about the explosion of a liquid? You say, well, it's hottest in the middle. It has highest pressure in the middle. What drives explosions of liquids is the gradients in the pressure, which the gradients in the pressure are strongest left to right, much less vertically. So if this is a liquid, it will explode like this. So there I've taught you to look at an explosion and see that it was a liquid that exploded. One can do this quantitatively and do a lot more work and extract from data like this with quantitative analysis this measure of the liquidness of this liquid, and you see that it gets down to around 0.3. Okay, now this is real data from the LHC. Let's look at it. It's 4 events from the LHC. These are the explosions. The red and the blue show us the direction of energy flow. This one looks pretty circular. A gas could have exploded like this. Look at this one, though. Much, much more explosive force this way, less this way. This one is pretty irregular also. This one is pretty irregular also. It's a liquid. Okay? So I've trained your eyes. You can now look at this data, and you can say, that is not a gas. Okay, I haven't taught you how to do this quantitatively, but we can. And you discover, doing this quantitatively, that this measure of liquidness for this liquid is between 0.1 and 0.2. This is the lowest value of this measure of liquidness for any liquid we've ever found. For water or milk, it's around 1 to 10. Gases, this is a dimensionless measure. 8 over S is actually very large for gases. So hot quark soup is more hydrodynamic than water. Hydrodynamics is named after water. Hydro is the Greek word for water. Hydrodynamics is the study of liquids, named after water. We have a better liquid than water. So what's the picture you should have about this soup? Quarks and gluons in the soup diffuse around. They're not bound up into protons, but they're also not free. They are not confined in the sense they're not localized in a proton. They can bounce, but you know, imagine you're in a crowded room and you want to get across the room. You're always bumping into your friends. That's what it's like for quarks in the soup. They're always bumping into each other. They're never free, but they're also not localized into protons. That is quark soup. That's what filled the universe for the first 10 microseconds after the Big Bang. And that's what our experimental colleagues reproduce in the laboratory every day in Geneva. So what does quark soup do? Pressure of 2 × 10⁻31 atmospheres. If it fills the entire universe, it expands and cools slowly. You've got a universe worth of it. Yeah, it cools, but it takes 10 microseconds to cool. But if you make just a little droplet of it in the lab, it explodes. There's nothing holding it in, it explodes. Those are the explosions we're studying, and the shape of those explosions tells you about the liquidness. So you look at data like this, you look at data like this, and you learn that it's a liquid. I have analogies to cosmology and condensed matter physics, but I will end the first half of the talk instead with a story. So in 1977, Vicki Weisskopf, a great theoretical physicist from a previous era, was giving an after-dinner talk. And his job in this talk was to honor his friend. Vicki was from MIT. His friend and buddy up the road from Harvard, Edward Purcell, was turning 60. And this was an evening honoring Edward Purcell. Edward had done research on liquids, and Vicki wanted to explain how amazing it was that Edward had made progress understanding liquids. Kind of like what Mark said at the beginning of the introduction, he wanted to say liquids are challenging. So he constructed an entire after-dinner lecture about how hard liquids are to understand. So let's read the beginning. Under ordinary terrestrial conditions, matter appears in 3 states: solids, liquids, and gases. Solids and gases are easy to understand. Liquids are harder. Assume that a group of intelligent theoretical physicists lived in closed buildings from birth such that they never saw the real world. They never saw natural structures. Parenthetically, let's forget that it may be impossible to prevent them from seeing their own bodies, their inputs and outputs. He was a bit of a jokester, Vicki was. What would these theoretical physicists be able to predict from a fundamental knowledge of quantum mechanics? So his setup is, take a bunch of theoretical physicists, we have many of them in the back here, lock them up in a room, give them the laws of nature, and say, what do they predict? What do they describe? These theoretical physicists, Vicki said in 1977, would probably predict the existence of atoms, molecules, solids, metals, insulators, gases. Most likely they would not realize that liquids were a possibility. So Vicki was right. He wrote this in 1977. All the theoretical physicists on the planet Earth had been given the laws of nature by David Gross in 1973. Nobody said they described a liquid. It took until the early 2000s when this liquid was recreated in the laboratory before we learned that actually these laws describe hot quark soup. So we could declare victory and go home. We've discovered the first liquid that ever existed. It's the liquid from which protons and neutrons formed. It's the hottest liquid that's ever existed. It's the most liquid liquid. But all great discoveries pose new challenges, and that's the second half of the talk. So what next? There's 2 directions you can go when you find a new kind of matter. You can ask about its phase diagram. I won't do that today. You can ask instead, well, how do those laws that David and Frank discovered in 1973, how do those laws actually, why is it that the whole world of theoretical physics didn't realize that they described a liquid? So how does the liquid emerge from the laws? So you want to probe the liquid to understand its inner workings. So you want to do what Rutherford did for atoms and what Friedman, Kendall, and Taylor did for protons. The first step to seeing how this works is, can you see, in quotes, the individual quarks and gluons in the liquid? We need some high-resolution, fast shutter speed way of looking at one quark or one gluon at one moment. That's what Friedman, Kendall, and Taylor did. Okay, so please, I see one experimentalist in the room. I'll pick on Yenji. If there's another one, if there's another experimentalist, they're spared because I haven't spotted them. I go to Yenji and say, Yenji, you're making drops of this liquid at CERN. Could you please take a drop of the liquid, bring it over to Stanford, and shoot the electron beam at it, and just do what Friedman, Kendall, and Taylor did? He says, well, Krishna, my drops of liquid only live for 10 to the minus 22 seconds. There's no time for me to bring them from Geneva to Stanford. So here's the idea. You go back to this picture. We focused last time on the electron being scattered off, but think about this quark that you Yenji just clobbered and kicked to the right. Imagine now that this proton is inside the soup, or this proton is in the collision that is making the soup. You've just kicked a quark very hard to the right. You think of this quark as your probe. That's the idea. And this is how it actually looks in data. So this was one of those collisions. But in the same collision that made the soup, all these yellow lines are the debris of the soup. In that same collision that made the soup, there was a quark from one proton hitting a quark from another proton, and they both bounced off at large angles. And you see this spray coming out this way is the debris of one quark. This spray coming out this way is the debris of the other quark. These jets of particles, the debris that you get when you kick a quark really hard, there's two of them here. This one and this one. So that was data. This is cartoon. You collide two lead nuclei at CERN. You make a blue blob of liquid. Right at that red star, obviously cartoon, right at that red star, there was a quark that hit another quark really hard. This quark went this way. This quark went this way. Quarks don't come out in isolation. They come out as these sprays of particles. These are called jets. So we're going to be looking at jets for the next 10 minutes or so. This is the cartoon of a jet. This is what jets look like in Yenji's detector. So why jets? Why is it interesting to look at these jets? We want to look at the inner workings of this soup to see how the liquid is put together. We need probes with fine resolution. And jets provide the best chance that we have of, if I go back to the cartoon, suppose that this quark in the spray, as it's going through the soup, scatters at 30 degrees. That'll change the shape of the jet. It's all of a sudden got an extra branch. That's Rutherford. It's our version of Rutherford. That's what we're going to try and look for. But you have to look for it in this. But there's another thing that jets do. If I go back to the cartoon, this jet going through here makes waves in the liquid. You're shooting this thing through this blue liquid. It makes waves. That's actually very interesting also, but for our Rutherford goal, it's a complication. So it's not easy to decode the wealth of information that's encoded in data, but that's what we're going to talk about. So first of all, is this real? Is this fiction? This is one of those events sort of unrolled onto a sheet of paper, and you see a jet here and a jet there. So this is another way of representing something like this. You see a jet here and a jet there. You unroll that onto a sheet of paper, and this jet has energy 205, and this jet has energy 72. Is energy not conserved? Is momentum not conserved? I've got two back-to-back jets. This one is 205, this one's 72. Well, what's happened here is that this jet lost more energy because it went through more soup. This jet lost less energy. So this is the 205 and this is the 72. So again, I've trained your eyes. You look at the data and you say the jets are losing energy, because this one has 75, this one has 205. So this is real. Theoretical, I've been giving a lot of credit to experimental physicists, and that's fair, but theoretical physicists are useful too. This is the Kavli Institute for Theoretical Physics. So theorists, in terms of the goal of doing this Rutherford experiment, theorists are taking key steps And I'm going to focus on two key, there's four listed here, but I'm going to focus on two key steps that theoretical physicists in this room have taken in the last very recent times, actually. I'll come back to this slide multiple times. And I'll explain what those two key steps are. I also want to explain for you what a model means. So for the next period of this talk, I'm going to be using a model for everything that I do. What good are models? Where's Mark? Mark said this is hard. Yeah, it's hard. If I knew how to do these calculations absolutely correctly from first principles, I would, but I don't. Nobody does. So you build a model, which I'm going to describe. And one of the really nice things about a model is that in a model, you can turn physical effects off and on that you can't do in nature. And so if we want to say, what are the effects in the data of Rutherford scattering? In a model, I can turn it off. In nature, you can't. What are the effects of the wakes of the jets, the waves in the soup? In a model, you can turn it off. In the real data, you can't. And so we're going to, in three different ways, the first one I'm going to give very short shrift to, but I included it because Yenji's in the back row. We're going to use the model to turn it off and on three different things and learn three different things. What's the model? I just wanted to put a whole bunch of names here. It includes Guy, who's in the back there, Danny, who's in the back there, and many others, as you can see. This model you can think of like the centaur of mythology with the head of a something on the body of a something else. If this were a scientific seminar, I'd have to spend a lot of time defending the crazy choices that we've made because we describe how the jet forms with traditional QCD methods. We describe the liquid with hydrodynamics. We describe how the liquid interacts with the soup using calculations from a cousin of QCD that were first done by string theorists. And then we describe the Rutherford scattering itself with traditional calculations again. This is four different kinds of calculational methods all glued together. It's not a first principles, all details correct calculation. It's a model, but this will allow us to train our eyes. Okay? I've trained your eyes twice in this talk. You can think of what we're going to do now as training our eyes, us, the theoretical physicists, training our eyes. First of three uses of the model, this one quick. How do you look for wakes in the fluid? I won't do this justice, but I included it because what I'm including is results that Yenji Li, back row, first showed at a conference in 2024. So we're now up to 2024 in the history. I won't describe two other ways of doing it that I and my collaborators have proposed. So when you say waves in the liquid, this is what a theorist thinks. I have a jet shooting through this liquid. It's going from bottom to top. It makes sound waves, and it makes a wake. This is a calculation by me and some friends, including Guy and Danny, who are in the back over there. And you see, shown here, yeah, there's a wake. This volume of liquid is moving upwards, following the jet. If you have a duck on water, the water behind the duck is moving.
Could this be constructive, destructive interference between the particles?
There can be constructive, destructive interference, in particular over here, although it won't be relevant for what I'm going to do. But yes. Okay, so I told you this is how theorists think. This is not, Yenji doesn't look and see waves like this. What does Yenji do? So what Danny says is you take this calculation and you ask, what's the meaning of moving liquid in a particle detector? Well, if there's liquid that's going this way, let me use the stick. If there's liquid that's going this way, that translates into an excess of particles in this direction and a deficit in this direction, in the opposite direction of the moving liquid. And that's what Yenji found. So he looked at events where he had a single jet back-to-back with a Z boson, so not two jets, just one. And blue is what you would expect without the effect I'm talking about, and you see an excess of particles here in red, and you see a deficit here. Well, is it what we expected? Danny, using the model I've described, Danny had done these calculations before he saw the data, The solid blue curve is Danny's calculation, including the wake, and the dashed blue curve is no wake. You can see this is discovery science. The uncertainties are still large, but you can totally see that the no wake hypothesis is ruled out. There really is a wake in this liquid. This is a discovery from 2024. And I'll skip this. So this was the last slide of Yenji's talk announcing these results. Unambiguous evidence of the wake created by a fast-moving quark. He referenced a duck on the water. This was sort of an artistic impression of the blob of quark-gluon plasma with a wake in it. And then he showed this picture. And I want to reflect on this picture for just a second. If this was the right way of thinking about what we're doing, forget about doing a Rutherford experiment. This would be bad news. This is a bullet going through an apple, and the bullet is blasting its way through the apple. It's making a wake, fine. But you're never going to see this bullet deflected by 30 degrees. Because this bullet doesn't study the atomic structure of the apple. It's too big. Question. When a jet shoots through the soup, can you see the soup interacting with the jet in such a way that it's not just one bullet shooting through, but you can see the individual quarks in that jet interacting one at a time with the soup? And this is, I didn't put the date, but this is 2025. First unambiguous evidence, I would say, I'm a co-author of this, but I would say first unambiguous evidence that the answer is known now. Green here is what you would expect for this observable if jets were bullets. Green is jet as bullet. Jet is a single object. It'll never be deflected. And the data, which are these gray boxes, disagrees. Red is the jet, every quark in the jet behaves individually. Not quite right. The in-between case where quarks see two quarks, the soup sees two quarks as separate if they're more than this distance apart, that's what describes the data. And this is very promising. This says that quark-gluon plasma, the soup, can respond to substructure within jets. It can see the individual quarks in a jet, and maybe we can see one of them scatter by 45 degrees. So how do we look for that? Now, I apologize. This should be called Rutherford scattering. It's not called Rutherford scattering because Rutherford scattering is non-relativistic. It's called Moliere scattering. You're going to see Moliere on slides. I had to introduce the word. Moliere is another a physicist who first studied this in the 1930s in a very different context. We're now going to take our model and we're going to add Rutherford scattering. We're going to add the possibility that those high-energy quarks in the shower can see the point-like object in the soup. We're going to look for large-angle scattering. It's just like Rutherford. It's named after Moliere, but it's just like Rutherford. So what measurements should we make to see this? So what we do, we take our model, we add this effect, and then we can turn it off, turn it on, turn it off, turn it on. Some of us in the room, including me and Danny and Guy, have been trying to figure out how to do this for about 5 years. And we've been stymied by the fact that in lead-lead collisions, there's a confounding effect, an annoying confounding effect. So what are we looking for? Need my hands. I have this developing spray of particles, and one of them gets kicked by 30 degrees, 20 degrees, 40 degrees. That makes the spray wider because I just made an extra branch. That's what we're looking for. Well, there's an opposite effect, which is that those jets that are wider lose more energy, so you don't see them. The jets that you see are the narrowest ones. So when you send 1 million jets through the soup, the ones you see are the narrow ones. That means in lead-lead collisions, the jets you see are narrower. That's the opposite effect that we're looking for. So one of the problems we've been wrestling with is how can we find how can I tell Yenji what to look for? if when he looks in the obvious way, he sees the opposite of what we're looking for. July 2025 and February 2026, oxygen nuclei were collided at the LHC and at RHIC. February 2026 was the last data taking at RHIC. So RHIC began in the year 2000. The last day of collisions at RHIC was February the 6th, 2026, about a month ago. And the last week of RHIC running was oxygen collisions. The LHC ran oxygen collisions for the very first time in July 2025. Why are we interested in oxygen collisions? Well, there are other people who have other reasons, but I'm interested in them because I think this is the best way of doing the Rutherford experiment. We have to first show ourselves that jets do lose energy in oxygen collisions, but then they're going to lose less because oxygen is much smaller than lead. So the confounding effect will be less. That gives us a chance of seeing what we're after. So the very first measurements taken last July, this is sort of this is the way that jet quenching was discovered at RHIC in the year 2000. This is a discovery measurement. It's just counting the number of particles with a given momentum. It's sort of the most crude way of seeing that the fact that this ratio is less than 1 is the most crude way of seeing that jets are losing energy. And we look at it with our model. Blue is what we get without Rutherford scattering, without Molière scattering. Red is with. If our model was truth with a capital T, this is definitive. Because our model cannot come close to describing the data unless we include this Rutherford scattering effect. Our model is not truth. So this is an example of a model-dependent comparison. This comparison, you'd have to believe our model was truth to say that this was the discovery of Rutherford scattering. So we want something better than that. But it's certainly good motivation. So the challenge is then, what's a distinctive observable? What's something that you can't see any other way other than jets sprouting extra prongs? So this is the first example. The second one's on the next slide. I'm going to show a bunch of plots, all of which have red, green, blue, and black curves. Red is the prediction for nature. Green means turn off jet wakes. Blue means turn off Rutherford. And black means turn them both off. So no experimenter can mess with nature. They can't turn things off, but we can. And what you see here is that the effect of wakes, green, is the difference in red and green is pretty small. So jet wakes are not too bad of a confounding effect here. What you also see, if we did this in lead-lead, I won't show you, but the blue and black curve would be way down here. That's the confounding effect. The confounding effect is much, much less. These blue and black curves are very close to 1. What does 1 mean? 1 means it's just as likely in oxygen as in proton collisions to see jets with two prongs separated by this angle. And what you see is that in oxygen collisions, it's more likely. Oxygen collisions, the jets grow extra prongs with these angles. So Yenji, where are you? Can you measure that, please? Okay. Yenji says he can do it. If his data ends up here, he's discovered Rutherford scattering off of quarks in the soup. If it ends up right on the line, I'll be disappointed. Here's another such observable. I won't describe it in as much length, but same idea. Red and green up here. Here's a third one. Bumps. There's a bump here. It's at about 0.5 radians. That's 30 degrees. We're telling Yenji to please go find this bump. And this bump is the scattering angle. It's about 30 degrees. This is saying that in oxygen collisions, we predict that there should be certain jets in which quarks scatter at 30 degrees. Or there's a distribution, but peaked at 30 degrees. And if I look at higher energy jets, the angle gets less. Higher energy jets, 20 degrees. There's a quantitative prediction. Yenji, please go measure. Rule us out. If you see something that looks like this, that's the discovery of quark. That's like what Friedman, Kendall, and Taylor did for protons. That's the analog for quark soup. So I claim that the next several years are going to be the golden age of this science. We're going to learn about the microscopic structure of QGP, and we're already learning about its ripples. So Lars is standing up there. I was always going to skip this. I did want to say a couple of words about cold quark soup. Much fewer words, Lars. Nah, I'm doing cold quark soup because I'm doing cold quark soup. So there's growing evidence that at the centers of neutron stars, the pressure of neutron stars as a function of density has this kinky shape here. The evidence for this comes from data that Lars knows much better than I do. It comes from theory calculations that I know better than he does. They're all being put together to understand the pressure inside the center of neutron stars. And if you plot it in a different way, I think we're now sure that boring garden variety neutron stars with a mass 1.4 times the sun have neutrons all the way in. And 2 solar mass neutron stars, there's growing evidence that they have quark matter cores. And my graduate student, Rachel Steinhorst, who's sitting in the back there, and Alexei Korkula, who's coming here in a couple of weeks, and I have used this logic backwards. This is a slide from Alexei Korkula. He pointed out that we're taking the logic in the opposite direction. When people made plots like this, they were using theory calculations to learn about neutron star matter. We can now use neutron star matter to learn about theory. And what we did was to say, let's take all this astrophysical information that Lars and his friends discover with telescopes and LIGO, and let's learn about the pairing between the Cooper pairs in cold quark matter. And we have the first empirical study of the properties of cold quark soup. And I knew I wouldn't get through this, Lars. But the message that I wanted to leave you with, the second last message, the last message will be even quicker, is that there's growing evidence that 2 solar mass neutron stars have cold quark soup in their cores. Rachel and Alexei and friends are using a combination of astro data and theory to learn about cold quark soup and its sort of condensed matter physics properties. Last message, there's quark soup in this room. Exactly. In every proton. Every proton in the universe formed from the Big Bang, 10 microseconds after the Big Bang. It formed from quark soup. These folks, not from my community, but these folks have calculated the pressure inside a proton. They make plots like this. This is pressure inside a proton. I read their plots, and I notice that the pressure inside a proton, calculated from first principles by these folks, is around the pressure just above the pressure of the quark soup that the protons were made of. The quark soup that the protons were made of had this temperature. The pressure inside a quark is the pressure of hot quark soup at this temperature. So you should think of a proton as, at the beginning of time, 10 microseconds after the Big Bang, you grab a little bit of quark soup and squeeze it into a proton. That's what happens. 10 microseconds after the Big Bang, that's the birth of every proton. That poses interesting questions. What about entropy? You can ask me about that afterwards if any of you are interested in entropy. But there's a new accelerator being built in Brookhaven called the Electron-Ion Collider. It's going to scatter. This is a proton coming in. There's an electron over here. This is the Rutherford experiment off of a quark in the proton. This is that debris that I showed you from 1968. Okay? Electron clobbers the quark, makes a spray out here. We've seen that. What you can do at this new facility, though, when it's built in the 2030s, is to look at the other stuff quantitatively. And this will be the first opportunity to look at the strong short-range correlations inside a proton that are the fundamental explanation for why quark gluon matter is a liquid. So basically, by learning about this liquid, we've thought of a new way of doing the study of the interior of the proton that I think in the 2030s will allow us to close the circle. Okay, this experiment is very, very similar to what was done in the 1960s, except at much higher energy and with a detector that has more capability. And this will give us, I think, direct access to strong short-range correlations inside a proton, which is to say we will be looking inside quark gluon matter under pressure inside of a proton. And I think there's a really fruitful connection between the way you think about quark soup and the way what we've been doing with jets and what Yenji's going to show us next in a few months, maybe a year, and what we'll be able to do in the 2030s. And I wanted to end with that. So I've told you about quark soup in 4 contexts. In the early universe, actually, I'll go to the last slide. In the early universe, first 10 microseconds after the Big Bang, whole universe quark soup. At these experiments, you recreate a little blob of it, and it promptly explodes. And measurements of those explosions are allowing us, for the first time, to probe the microscopic structure of the primordial matter from the Big Bang. Cold quark soup is very interesting also. I didn't have time to do it justice. And then the last point, quark soup inside a proton. I would say we are just beginning to learn the lessons. From everything we've learned about hot quark soup, science goes in a circle. It's going to teach us new ways of learning about what goes on inside protons, and that will be the science of the 2030s. There will be a program here. I won't be necessarily here for it. Maybe Yenji will organize it. Danny will organize it. Alba will organize it. On what we're learning from this new accelerator about the quark matter inside of a proton. And I hope that the friends of the KITP will have been just as generous in their support over the next decade as they were in the previous one. And I will stop with that.
When you collide protons and neutrons, you get a spray of stuff. But you said there was like two quarks and a gluon inside of the particle. What makes up a whole big spray of stuff?
Very good. So the glib answer is E equals mc squared. That's what I was trying to describe with the metaphor of the rubber band. When you try to separate, when you clobber one quark and you try to separate it out from the rest of the proton, the forces between the quark and the debris are so strong that there's so much energy associated with this separation. So now I'm going to take E equals mc squared and turn it into m equals E over c squared, that the energy that comes from that force field is turned into mass, and you get a spray of new particles. That's a slightly more technical way of saying the rubber band breaks into shards, and each shard of the rubber band is a new particle. I don't know which explanation you like better.
John, just speak up.
Yeah.
What would the implications be for the evolution of the universe if early, just after the Big Bang, the quark soup was affected by asymptotic freedom just a little bit different than what it is? In other words, how fission it is.
Oh, that's an excellent question. If you changed what I was talking about only by a tiny amount, I don't think it would have major effect on the evolution of the universe unless you did something tiny with great consequence, which I'm not going to think of right now. The basic message is that this is not a good way to learn about the evolution of the universe on universe length scales. He knows how to do that you do that with telescopes. This is how you study the material properties of the stuff that filled the early universe. And he can't do that with telescopes. So telescopes tell you about the expansion of the universe and its macroscopic dynamics. That's a different talk. But we are the ones who know how to learn about the materials properties of the stuff, which telescopes don't tell us about. So there's a complementarity here. And I would not claim that what we're doing is going to influence our knowledge of the overall evolution of the universe.
Well, maybe this answers my question. You said you're making mini Big Bangs, but that's still orders of magnitude away from looking at things that would be like quantum gravity.
Yes. Many, 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 many orders of magnitude. Many, many orders of magnitude. Depending on if we use temperature as the way of assessing it, something like 15 orders of magnitude.
Oh my God.
So I may not have done the arithmetic quite right, but nowhere, long way.
Right.
There's a very interesting connection between things that string theorists have learned how to calculate and things that we're interested in, but it's not that. We're nowhere close to doing quantum gravity in the laboratory.
When the rubber band breaks, what are the particles?
Oh, well, they all have names. I've been avoiding names. They're pions, they're kaons, they're lambdas, they're omegas. They all have names, but me telling you the names, I don't know that that helps you. Each one of these particles, like the pion, so a proton is 3 quarks. A pion is an up quark and an anti-up quark. Kaon is an up quark and an anti-strange quark. I'm not sure whether me giving you the names to things helps you, but each particle is made of a different flavor of quark, and the sort of periodic table of these particles is what first gave people a hint that there must be quarks. That was the very beginning of the talk, but I avoided telling you the names of all of the particles on that periodic table.
That's the alphabet soup.
That's the alphabet soup.
Okay, well, I think we couldn't have a better example of how breakthroughs in experimental physics keep the theorists honest. Thank you.